Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
A virtual work for this particular problem want to determine or to show that when the center of gravity is above the centroid, okay, that the equilibrium will be unstable. Okay, let this point be our G. Okay, let G be here initially here. Okay, the centroid be here. Then if there's a rotation, the G now comes here. All right, and we can just trace this to the center. All right, let's call this place arrow from here to here is the radius. This is also still the radius. Okay, it just moves like that. All right, and G, you can trace this G down, and G was originally passing through here. All right, so the angle theta, this angle theta created, and this height was initially here, okay, which is to this point. Let's call it h. All right. Then from the okay, the datum there, we have this to be here to be y. Okay. All right. And of course, we know that this height also is also arrow. All right. To solve the problem, what we do is to determine the the potential function, the potential energy function, and differentiate it with respect to theta. Okay, all right, and determine the position. Okay, theta, and proof for stability. Okay, determine the stability by taking the second derivative. Okay, differentiating the function the second time and solving to determine the stability. All right. Of course, plugging in theta. All right, that will achieve. This is W. This is also okay. The mg equal to mg. All right, and this is g here again. Okay, and h. This place from this point to this point now is now our h. So let me just trace it to this side. H. All right, that was originally here. It's not as okay. So that's h. All right. Then we can just go ahead to get y. So y is going to give us equal to h cos theta, as you can see from there, plus arrow h cos theta plus arrow. So if we do this, uh, of course, v, our potential gravitational potential energy is going to be, which is v subscript g, is going to be is positive, so it's going to be w y. So if we plug in values into here, v is going to give us w wh cos theta, cos theta, okay, plus wr, okay, plus w W arrow. Okay, so that's what we are going to get. Actually, this actually stems from this, that b is equal to, okay, is equal to w, okay, into h, okay, cos theta, okay, plus arrow. Okay, so that's how we got that one. All right, all right. So if we look at the equilibrium position, we are going to have the v, the theta, to be equal to 0. So if we solve this, it's going to give us minus w, okay, h sin theta to be equal to 0. Okay, so that sin theta will be minus w h, okay, equal to 0. So that sin theta, okay, sin theta will be equal to 0. So that your theta, if you take your arc sine, is going to give you 0. Okay, so it's going to give 0. Of course, for the stability, we'll take the second, we'll differentiate that potential energy function again with respect to theta. So we'll have this. All right, if you do that, you will have this to be minus wh cos theta. Okay. All right, so that's what you're going to have. Now, if you put cos theta, put theta to be equal to 0 degree into here, we are going to arrive at minus w h. Okay, and if you look at minus w h, you can see that this is clearly less than 0. So that tells us that the equilibrium is is uh, is unstable. Okay, unstable equilibrium, and you know that this one is actually the same thing as sorry, same thing as mg. Okay, same thing as w, same thing as m, the mass times gravity h. Okay, so any one of these is correct, but the equilibrium is unstable. So that's it.